Hello, welcome back to the lecture series on frequency domain analysis. So we have completed two lectures so far, and this is the third lecture. The learning objective for this lecture is understanding various frequency domain specifications. So before going into this lecture, let us have a quick review of what we learned in the previous lecture. The first lecture, we understood the concept of frequency domain analysis. We understood that the frequency domain analysis is a steady state analysis. And if I have a system represented by g of j omega, the gain at a particular frequency omega, and if that system is given an input a sine omega t, the output will have the same frequency, but the amplitude will be multiplied by the magnitude of this j of j omega and an angle equivalent to or equal to this angle of g of j omega will be added to this the phase of the signal. So a signal will undergo a change in the magnitude and the phase angle, and it depends only on this g of j omega. Therefore, to understand the input output relationship for a sinusoidal input, it is just sufficient to understand how this g of j omega varies with respect to frequency. So we tried plotting this g of j omega with respect to frequency in various modes, and we understood about the 5 different plots, and among the 5 different plots, these are the 3 important plots. That is what we understood. So the Bode plot, in which the gain in decibels is plotted against the frequency in logarithmic scale, and the phase angle also in degrees is plotted against the frequency in logarithmic scale. These two subplots together form the Bode plot, and the polar plot is usually drawn on a polar graph, and it traces the ends of the phasors which move as the frequency varies from 0 to any specific value. And this polar plot is sometimes called as Nyquist plot also, because the Nyquist is the one who proposed this way of representing the frequency response. And we learned about the other frequency response curve, which is nothing but the magnitude in decibels against the phase angle in degrees, and it is drawn in a background called Nyquist chart. So these are the major frequency domain plots we understood in the previous lecture. So having understood this, it is a time to understand the different frequency domain specifications. When you study the time domain analysis, you might have come across various time domain specifications, such as the rise time, peak time, settling time, peak overshoot, and such stuff. So similarly, when I represent something as a plot, I should characterize that plot with some specifications. So here also, in this frequency domain also, I got a few plots, and therefore these plots I can characterize using some specifications. Okay, those specifications are what we call it as the frequency domain specifications. So these are the frequency domain specifications: the resonant frequency, the resonant peak, cutoff frequency, bandwidth, cutoff rate, gain crossover frequency, phase crossover frequency, gain margin, and phase margin. And these are the specifications we are going to focus in this lecture. So among these specifications, I can group them. I can group the specifications into 3 different groups. The first two specifications, I can put them together, and the next 3 I can put them as together, and the last 4 I can put them as together. 2, 3, and 4. So we will study all these specifications in 3 groups. This lines show the division of these specifications. To understand these specifications, I have taken the Bode plot of a prototype second order system. Okay, so especially I have taken the magnitude plot, and you are able to see that the magnitude plot contains the gain in decibels in the vertical axis and the frequency in radians per second on a logarithmic scale. The initial value I have taken is 0.1, 1, 10, 100 and 1000. So this is what we call it as a semi-log graph, and in the semi-log graph this division from 0.1 to 1 or 1 to 10 or 10 to 100 is what we call it as 1 decade. This distance is what we call it as 1 decade. Okay, anyhow, please note that this 0 decibels corresponds to a gain of 1 and minus 20 signifies a gain of 0.1 and minus 40 signifies a gain of 0.01 and minus 20 corresponds to 0.001 and minus 80 corresponds to a gain of 0.0001. Okay, so now let us define these specifications. The first specification is the resonant peak. Resonant peak is nothing but the maximum value or the maximum gain of the system over the given frequency range. That is what we call it as the resonant peak. So at this frequency, if the input frequency matches this frequency, the output will have the maximum value because the gain is maximum, and therefore the output magnitude also will be maximum at this frequency. So the frequency at which this resonance happens, frequency at which it reaches the resonant peak, is what we call as the resonant frequency for the given system. For the example system which is taken, the resonant frequency is 10 radians per second. That means if I give an input sinusoidal signal with a frequency of 10 radians per second, then the magnitude or the amplitude of the output will be maximum. That's what it means. So the resonant peak and resonant frequency can be expressed with this expression, and this expression contains the variables zeta and omega n. Zeta is the damping ratio and omega n is the undamped natural frequency of oscillations, and these parameters you should be well aware of when you studied time domain analysis. Please note that this particular expression is valid only for zeta values lesser than or equal to 1 by root 2, because if zeta is equal to 1 by root 2, the zeta square becomes 1 by 2, and 2 into 1 by 2 becomes 1, that is 1 minus 1, 1 minus 1 is 0, and therefore omega r will be equal to 0. And for any value of zeta greater than 1 by root 2, this will be greater than 1. This 2 zeta square will be greater than 1, and therefore this square root will become a square root of some negative number, and the entire quantity will become an imaginary number. But what is here? This is omega r, this is resonant frequency. Frequency cannot be an imaginary number. It has to be real. So therefore, for any value of zeta greater than 1 by root 2, this expression is not valid. And if this expression is not valid for zetas greater than 1 by root 2, this expression, the corresponding resonant peak expression, also will not be valid, and therefore both these expressions are valid for theta values lesser than or equal to 1 by root 2, which is equal to 0.707. So what if the theta value is greater than 0.707 or 1 by root 2? Then it means that, as I said, even for 1 by root 2, the resonant frequency becomes 1. Sorry, resonant frequency becomes 0. It is 0. So, at 0 resonant frequency, whatever value is going to be for the gain is going to be the resonant peak, and for a prototype second order system, that resonant peak is going to be 1. Okay, or 0 decibels. In decibels, it is going to be 0 decibels. So if the theta value is greater than 1 by root 2, then omega r is 0, the resonant frequency is 0, and the resonant peak is going to be 1, or it is going to be 0 decibels. And the second point is, omega r and omega n are not always equal. See, they are related by this expression. They become equal only when theta becomes equal to 0. When theta becomes equal to 0, then omega r becomes equal to omega n. Alright. So when theta equal to 0, it means that the system is an underdamped system. Therefore, for an underdamped system, the resonant frequency is nothing but the natural frequency of oscillation of the system. And you can notice there is a specific correlation between the resonant peak and peak overshoot. Please note that the resonant peak is a frequency domain specification, and the peak overshoot is a time domain specification. So this is the expression you will be able to recall for the peak overshoot, and this is the expression we have given for resonant peak. In both the expressions, if the theta value is more, then MP will be more and MR also will be more. What does it mean? For lesser damping ratio, the resonant peak will be higher and the peak overshoot also will be higher. So just remove this. It implies that higher resonant peak means that higher peak overshoot. It's really interesting because the sinusoidal steady state analysis gives some clue about the transient analysis for some step input or impulse input or anything. So the resonant, so if you notice some frequency response with higher resonant peak, then immediately you can understand that in time domain that system will have a peak, higher peak overshoot. So this is the correlation between the frequency domain and the time domain specifications. Anyhow, this figure shows the variation of resonant peak and the resonant frequency with respect to, for different values of theta or the damping ratio. When theta is equal to 0, that is for underdamped system, this resonant peak will be infinity. That you will be able to notice here. See, MR, when theta is equal to 0, it will be 1 by 0, which is going to be infinity. And also, you will be able to notice that at theta is equal to 0, omega r becomes equal to omega n. So at theta equal to 0, which is this dotted line, the resonant peak becomes infinity and the resonant frequency is equal to omega n. So 1 signifies this x-axis is the omega values normalized by omega n. All the omega values are divided by omega n. Therefore, this 1 corresponds to a omega value of equal to omega n, and therefore at when theta is equal to 0, this resonant frequency is same as the natural frequency of oscillation omega n. But for theta values greater than 0, see, the resonant frequency falls slightly below the natural frequency. So when the theta value increased, the distance between the natural frequency and the resonant frequency is larger. It increases as theta value increases. This corresponds to theta is equal to 0.5 and this was 0.3. And when the theta value increased beyond 0.707, otherwise 1 by root of 2, there is no peak here. The peak is only 1 and it happens at a frequency of 0. So that is what we were discussing in the previous slide. So we have understood what is meant by a resonant peak and the resonant frequency, and also we understood how the resonant peak and resonant frequency are related to theta. Now we will move on to the next set of specifications. So we'll start with this cutoff frequency. To find the cutoff frequency, what you need to do is draw a line at -3 decibels. The frequency at which this gain becomes -3 decibels is what we call it as the cutoff frequency, and it is denoted by omega c. Now let us see what is meant by bandwidth. Bandwidth is a range of frequencies. It's not a single frequency, it's a range of frequencies for which the magnitude of the system or the gain of the system is higher than this -3 dB. See, for this entire range of frequencies, the gain of the system is higher than -3 dB. That's it. So you understood what is meant by cutoff frequency, what is meant by bandwidth. Now there is one more specification related to this, that is cutoff rate. Cutoff rate is nothing but the slope at this point. You know, the slope is represented by the fall or rise in decibels per decade. So this cutoff rate, that is nothing but the slope of this plot, gain plot at this cutoff frequency will be expressed in decibels per decade. So this bandwidth also has got an expression. Anyhow, the derivation of all these expressions, whether it is resonant peak or resonant frequency or this bandwidth, I have not given. You can refer any standard book on control systems and you will be able to see the derivation. So this is the expression we can derive for a prototype second order system for the bandwidth. So what if the system has got, if the system crosses this -3 decibels line at 2 points, in that case we have a lower cutoff frequency and we have got a upper cutoff frequency, lower cutoff and upper cutoff frequencies, and within this frequency range the gain is going to be greater than minus 3 decibels. So this frequency range, we will call it as the bandwidth. Please note I have used the notation F here instead of omega. In the frequency axis, the frequency can be taken as radians per second as angular frequency, or in cycles per second, or in hertz. The frequency can be represented in any unit. So whether omega or F, it doesn't matter. Now we will have a question. Why this minus 3 decibels? Why not 5 decibels, or why not 10 decibels, or why not minus 10 decibels or anything? Why specifically minus 3 decibels? Let me explain this. So you might have studied in signals and systems that power in any signal is directly proportional to square of it. Okay. For any signal to be useful, the power in the signal should be at least 50%. 50% means half. The minimum power should be half of it. The minimum power should be half of x of t square. This term I can write it like this: x of t by square root of 2 the whole square. So now assume that I am giving a signal x of t as an input to an LTI system, and if the system is assumed to be having a gain of 1 by root 2, the output magnitude of the output is going to be x of t by square root of 2. If I take the power for this signal, I will be getting this. What does it mean? If the gain of the system is 1 by root 2, and if I give a signal x of t, the output signal will have a power of 50% of the input signal. That is what it means. For any signal to be useful, the power of the signal should be at least 50%. Therefore, the minimum gain required for the system is 1 by square root of 2. So the minimum gain 1 by root 2, if I convert it to decibels, 20 log of that, I get 20 log of 0.707, and you will get the decibels value as minus 3.0102, which is approximately equal to minus 3 decibels. So therefore, we take the cutoff frequency as the frequency at which this gain becomes minus 3 decibels. Or if the actual gain is taken, then the corresponding gain, minus 3 decibels gain, is going to be 0.707. So this completes the explanation for the 3 specifications, that is cutoff frequency, bandwidth, and the cutoff rate. Now let us understand about the gain crossover and phase crossover frequency, and also about the gain margin and phase margin. For that, I have taken another system. It's a second order system. Sorry, it is a third order system, Bode plot. A third order type 1 system, Bode plot. I've taken both magnitude plot and the phase plot, because to find the gain crossover and the phase crossover frequencies, we need both the plots. So here is how the phase crossover and the gain crossover frequencies are explained. The gain crossover frequency is the frequency at which the gain becomes 0 decibels, or in actual, gain, it is 0 decibels corresponds to a gain of 1. So at which frequency the gain becomes 1, or at which frequency the gain becomes 0 decibels. That's what we call as the gain crossover frequency, and it is denoted by the letter simple omega GC. For the system which we have taken, omega GC is equal to 1 radians per second. Similarly, the phase crossover frequency is the frequency at which the phase of the system crosses minus 180 degree. Otherwise, the frequency at which the phase shift or the phase lag introduced by the system becomes minus 180 degree. Okay, so that is what is the phase crossover frequency, and it is denoted by omega PC. And for us, the system which we have taken, the omega PC, the phase crossover frequency is 35 radians per second. Now let us see what is meant by gain margin. See that at this phase crossover frequency, the gain of the system is minus 34 decibels. So if I want to make the gain of the system as 0 decibels, what should I do? I should add plus 34 decibels to it. So I have got a margin of plus 34 decibels. This margin is what we call it as the gain margin. Okay, and in terms of stability, when the gain margin or when the gain at the the phase crossover frequency becomes 1, it means that we are driving the system to the verge of instability. So therefore, the gain margin I can define in this way. The amount of gain in decibels to be added to the system to make or to drive it to the verge of instability. And let us see what is meant by phase margin. At the gain crossover frequency, the phase angle of the system is around 92 degree, minus 92 degree. That means at this gain crossover frequency, the phase shift is minus 92 degree, or the phase lag introduced by the system is minus minus 92 degree. So how much additional phase lag can I introduce into the system to make it minus 180 degree is a phase lag of 88 degree I can add, and that is what I call it as the phase margin. Phase margin. Again, when the phase of the system at the gain crossover frequency becomes minus 180 degree, again we may drive the system into the verge of instability, and therefore I can say that the amount of phase lag, I can define the phase margin as the amount of phase lag I can add to the system at the gain crossover frequency as the phase margin. So here we understood what is meant by gain crossover frequency, what is meant by phase crossover frequency, what is meant by gain margin, and what is meant by phase margin. And this phase margin has got an expression. You can note it. This expression is valid only for prototype second order system. Now let us summarize the frequency domain specifications we have been looking at. First one is the resonant peak. It is the maximum value of the magnitude of G of j omega. It can be in the actual gain or the gain converted to decibels. And the second specification is the resonant frequency. It's the frequency at which this g of j omega is maximum. And the cutoff frequency is the frequency or the frequencies at which this g of j omega is 3 decibels down the 0 decibels line, or the frequencies at which g of j omega is minus 3 decibels, and this minus 3 decibels is equivalent to a gain of 0.707 or 1 by root 2. The bandwidth is the range of frequencies during which g of j omega is greater than minus 3 decibels. Cutoff rate is the slope of the frequency response at the cutoff frequency, and it is given in decibels per decade. Gain crossover frequency, the frequency at which the magnitude of the Bode magnitude plot crosses 0 decibels line, and the phase crossover frequency is the frequency at which the phase plot in the Bode plot crosses the minus 180 degree, and of course in the plot minus 180 or plus 180 both signifies the same negative axis, so it can be said as plus or minus 180 degree. And the phase crossover frequency is repeated by mistake, and the gain margin is gain in decibels that could be added to the open loop gain to make the gain at the phase crossover frequency as 0 decibels, thereby to drive the system to the verge of instability. This is what I explained. And finally, the phase margin, it is the negative phase or the phase lag that could be added to open loop to make the phase at the gain crossover frequency as minus 180 degree, and this also will drive the system to the verge of instability. As we understood some time domain specifications in time domain analysis, we have understood some specifications in the frequency domain plots, which we call it as the frequency domain specifications. With this, we end this lecture. Thank you for watching.